Good morning, all of you. Welcome to CG and the Rank Zone. Today we are discussing lecture 4 in dilute solutions. In the previous lecture, we have discussed about colligative properties. Now, total there are 4 colligative properties. First one is RLVP, that is relative lowering of vapor pressure. Second one is elevation in boiling point. Third one is depression freezing point. Now the fourth one, osmosis and osmotic pressure. Let us see what is osmosis and osmotic pressure. This is the fourth colligative property. It is a phenomenon where the solute particles move from a region of high concentration, underline high concentration, you also underline. It is a phenomenon where the solute particles move from a region of high concentration to a region of low concentration. This is called diffusion, and this diffusion can be done by using semi-permeable membrane. It is a membrane which allows only solvent molecules to pass through it, but not the solute particles. Only solvent molecules to pass through it, but not the solute particles. This is called SPM. That is also called as semi-permeable membrane. So it is the one which allows the solvent molecules to pass through it, but not the solute particles. So this is called diffusion. Next. When a solution and solvent is separated by a semi-permeable membrane, the solvent molecules will move from the solvent side to the solution side. So this phenomenon in which the solvent molecules move from region of low concentration of solute to a region of high concentration of solute to SPM is known as osmosis. So I hope this is clear now. So what is osmosis? A process in which solvent molecules move from region of lower concentration of solute to a region of higher concentration of solute to a SPM is called as osmosis. So by applying pressure, solvent molecules, in the diagram you can see, by SPM, solvent molecules is flowing towards the solute molecules, where solute molecules is of low concentration and solvent molecules is of high concentration. So this is called osmosis, and the pressure applied to prevent osmosis, very, very important here. The pressure applied to prevent osmosis is called osmotic pressure. So it is a minimum excess pressure that has to be applied on the solution to prevent the entry of solvent into the solution through a semi-permeable membrane is called as osmotic pressure. So in general, simple words, write down all of you. The pressure applied to prevent osmosis is called the pressure applied to prevent osmosis is called osmotic pressure. It is denoted by the letter pi. It is denoted by the letter pi. So osmotic pressure is denoted by the letter pi. Pi. Yes. So this is called osmotic pressure. Simple words. And definition wise, if you see, it is the minimum excess pressure that has to be applied on the solution to prevent the entry of solvent into a solution through a semi-permeable membrane. This is called osmotic pressure. Next. Osmotic pressure is a colligative property as it depends on the number of solute particles in a definite volume of the solution. That's why it is also called a colligative property. So as it depends on the number of solute particles in a definite volume of the solution. It has been found that the osmotic pressure is proportional to molarity of the solution. Very, very important. The osmotic pressure is proportional to concentration of the solution or molarity, capital M of the solution. So pi is proportional to M, capital M. The M is called molarity. How to calculate molarity? Number of moles by volume of solution liters. Number of moles by volume of solution liters, N by V. So this we have done in concentration of expression concentration of solutions. Next, osmotic pressure continued. The expression for osmotic pressure is given by pi is equal to CRT, where pi is the osmotic pressure, C is the molar concentration. So instead of M, we have written it as C, and T is the absolute temperature. So pi is equal to CRT, that is also can be taken as N2 into R into T by V, where R is called gas constant R is called what? Gas constant, and its value should be taken as 2 when pressure is given in atmosphere, or 8.314. Generally, we'll take R value is equal to 2 here because pressure is given in atmosphere. So R value is equal to 2, where N2 is the number of moles of solute in volume V liters of the solution. But 8.314 will not use for R because we'll use R is equal to 2 in this case. Next. Using osmotic pressure data, the molecular mass of solute can be determined. If W is the mass of solute and M2 is its molecular mass, then N2 is equal to number of moles is equal to weight by molecular weight. So by using this, we can change the formula. Pi is equal to W2R into T by M2 into V, where M2 is equal to W2R into T by pi into V, where V is called volume, pi is called osmotic pressure, which we are going to find. And in this also, we can find out M2. So if volume is in cubic centimeters, we have to use 1000 also. W2 into R into T into 1000 by pi into V. That is volume given in ml or cc. You have to use 1000 also. Next, application of osmosis and osmotic pressure. Osmotic pressure measurements are used in determination of molecular mass of polymers. Very, very important. Molecular mass of polymers, because polymers are generally high molecular mass compounds. So osmotic pressure is used in the determination of molecular mass of polymers. The osmotic pressure measurements have an advantage over the qualitative property measurements in determining the molecular mass of macromolecules. So as the molecular mass of macromolecules is high, that is like polymers, the molecular mass is very high. The solutions used will be very dilute. Compared to other colligative properties, the magnitude of osmotic pressure is large enough for determination. So we'll use osmotic pressure so that the solvent molecules will not go into the solute particles, due to which we can find out the molecular mass of macromolecules such as polymers, which is of high molecular masses. So movement of water from soil into plants through their roots is by osmosis. Already we know this. Movement of water from soil into plants by the means of their roots is nothing but by osmosis. Preservation of meat by adding salt, as well as of fruit and fruit products by adding sugar, is due to osmosis, because the solvent molecules will flow into the solute particles. So that's why we can preserve meat by adding salt, and sugar, and we can store certain food products by adding sugar. I hope this is clear now. Next, water isotonic, hypnotonic, and hypertonic solutions. Hypotonic. So two solutions having same osmotic pressure, underline same osmotic pressure. Two solutions having same osmotic pressure. Same osmotic pressure is important here because those two solutions osmotic pressure is same at a given temperature are said to be isotonic solutions. Isotonic solutions usually have same molar concentration. If two solutions have different osmotic pressure, then the solution with higher osmotic pressure is said to be hypertonic, and the solution with lower osmotic pressure is said to be hypotonic. Hypertonic and hypotonic solutions with respect to each other. Again, I'm repeating. If two solutions have different osmotic pressure, then the solution with higher osmotic pressure is said to be hypertonic, and the solution with the lower value of osmotic pressure is said to be hypotonic solutions with respect to each other. So what are isotonic solutions? The solutions whose osmotic pressure are same at a given temperature are said to be isotonic solutions. Next. So for isotonic solution, pi is equal to same for both the solutions. That is osmotic pressure. What is reverse osmosis? If a pressure higher than the osmotic pressure of the solution is applied to the solution, is applied on the solution side, means what is osmotic pressure? The pressure applied to prevent osmosis. So if you apply pressure higher than the osmotic pressure of the solution is applied on the solution side, then the solvent will move from the solution side to solvent side, that is high concentration to low concentration of solute, through the semi-permeable membrane. This phenomenon is called as reverse osmosis. And based on this reverse osmosis only, we can do the drinking water we can make drinking water from seawater. Because seawater contains salts. So to purify seawater into drinking water, we will use the process called reverse osmosis, where we apply high pressure greater than osmotic pressure so that the solvent will move from the solution side to solvent side. that is from high concentration to low concentration. So you can see here reverse osmosis, applied pressure, pure water. So this is example, salt water, that is sea water is given. Salt water, if you apply pressure, what happens? By the means of semi-permeable membrane, some of the solvent molecules will flow through the solution, and so that we can have, see, you can round this one is called contaminants, so that will move from one side to another side by the means of SPM, by which we will get pure water. So the direction of water flow will be downwards and fresh water will be collected like this. So I hope this is clear. So this is called applied pressure and reverse osmosis. So as I told you, what are the applications of reverse osmosis? The phenomenon of reverse osmosis is used in the purification of water. Seawater is subjected to reverse osmosis to get potable water. Potable water means which is fit for drinking. Fit for drinking is called as potable water. So the osmotic pressure required is quite high and tougher semi-permeable membranes are used. Cellulose acetate membrane is one of them. So what is the SPM material is made up of? It is made up of cellulose acetate. Cellulose acetate is the membrane is one of them. I hope it is clear now. So this is called application of reverse osmosis. Next. Now questions related to osmosis. 200 cc. 200 cc means volume is given 200 ml. So V is equal to 200 ml over there of an aqueous solution containing 1.3 grams of protein. So yeah, weight of solute is 1.3 grams. The osmotic pressure of the solution is 2.6 10 to the power minus 3 bars. Pi value is also given. Calculate the molecular mass of protein. So we have to find small m. So we know pi is equal to C into RT. The R is called gas constant, T is called temperature. Temperature is also given. So C value, that is nothing but concentration, that is nothing but molarity, can be taken as that is also equal to weight by molecular weight, weight by weight of solute by molecular weight of solute, molecular weight of solute into 1000 by V into 1000 divided by V into R into T. So this is the actual formula of pi value. So in this, except molecular weight, we know all the other values. That is pi value, we know that is 2.6 in 10 to the power minus 3 bars. So 2.6 in 10 to the power minus 3 is equal to weight of solute, that is 1.3, that is protein weight, by X, we don't know molecular weight of protein, into 1000 by volume is given 200 ml into R value is 2 because atmospheric pressure is given. So 200, 300 and 100, 205 times. That is 5. So now X is equal to 1.3 into 5 into 2 into 300. 5 into 2 is 10. 10 into 300 is 3000. So 1.3 into 3000 or 3 into 10 to the power of 3, right? By 2.6 into 10 to the power of minus 3. So 10 to the power of minus 3 going to numerator, 10 to the power of plus 3. So 1.3 into by 2.6 into 3 into 10 to the power of 6. So 1.36, 1.32 times 1 by 2. So 3 by 2, that is 1.5 10 to the power of 6. So molecular mass of proton becomes 1.5 into 10 to the power of minus 6. So in this way, you have to solve this question. I hope it is clear now. 1.5 10 to the power of 6. So which is equal to 62,250, because 10 to the power of 6 also they are multiplied 1.5 10 to the power of 6. So after multiplying all these things, you will get 62,250 as molecular mass of protein. Next question. Calculate the osmotic pressure in pascals exerted by a solution prepared by dissolving 1 gram of polymer of molecular mass 1,85,000. That is 1,85,000 in 500 ml of water at 37 degrees C. They are asking us to find osmotic pressure in pascals. So already you know 1 atmosphere is 10 to the power 5 pascals. So 1 atmosphere. First we'll find the osmotic pressure in atmosphere, then we'll convert them into pascals. So pi is equal to C into R into T, which is also equal to W by M into 1000 by V into R into T. So R value is 2, we already know. So temperature is given 37 degrees C, change them into kelvins. So 273 plus 37, it is 300 kelvins. So now substituting the formula, pi is equal to W, that is 1,85,000. Sorry, 1 gram, 1,85,000 into 1000 by 500 into R into T. That is R value is 2, the temperature is 300. So solve for this, 2 times 0, 0, 0, 0 gets cancels. So 2 into 2, 4, 4, this is a 12 by 1850, 12 by 1850, 12 divided by 1850 is equal to 0.006, that is 6 into 10 to the power of minus 3, 0.0064 approximately, that is 6.4 into 10 to the power of minus 3 atmospheres. You have to change them into pascals. So this can be taken as 6.4 into 10 to the power of minus 3, 6.4 into 10 to the power of minus 3 into 10 to the power of 5, because an atmosphere is 10 to the power of 5 pascals. So 10 to the power of 2. So it will get around approximately 6,400, 6,400, 6,400, 6,400, 6.4 into 100 is 640, right? 640 is the answer. 27.86 pascals. I think they are given wrong. You can just check it out. The formula is same, because 1 atmosphere is equal to 10 to the power of 5 pascals is correct only. R value is 2 is correct only. 1 atmosphere 2 pascals. Okay. 1 atmosphere 2 pascals is 101325 pascals. Write down here. 1 atmosphere is equal to 101325 pascals. So since we got how many atmospheres? 0.0064. 6.4 into 10 to the power of minus 3. No need to write. 0.0064. 0.0064 into 101325 is equal to 648. Correct only. 648 approximately. That is not 27.86 pascals. This is wrong answer. Next question. 648 pascals is the right answer. Next. So we have done Colligative properties. Next topic in this chapter. Abnormal molecular masses. When a solute is dissociated in a solution in it produces more number of particles than expected. This high number of particles will lead to higher value for colligative properties. The molecular masses calculated using these higher values of colligative properties will be less than the actual molecular masses. So, will be less than the actual molecular mass. So, this is nothing but abnormal molecular masses. In simple words, I'll tell you. Till now, we have seen when a non-volatile solute is dissolved in a solution. Non-volatile solute means like urea, glucose, cane sugar, benzene, etc. All these are called non-volatile solutes. And when you dissolve a non-volatile solute, they do not dissociate into ions. They do not dissociate into ions. That is, if you dissolve glucose in water, glucose will not form ions. Similarly, urea also will not form ions. Benzene also will not form ions. Means they will not ionize. But what happens when you dissociate electrolytes? Because non-volatile solutes we have seen so far non-electrolytes only. But when you dissolve electrolyte, like for example, if you add some amount of sodium chloride in water, what happens? So that is also a solute. Sodium chloride is solute and water is solvent. And in this case, sodium chloride dissociate into Na plus and Cl minus in water. So when these electrolytes are dissolved, then the colligative properties will change because they are dissociating into ions. Whereas if you dissolve non-electrolytes, they will not dissociate into ions. Whereas if you dissolve electrolytes, they dissociate into ions. So all the colligative properties will change. So that is nothing but the topic is called abnormal molecular masses. The molecular masses calculated using these higher values of colligative properties will be less than the actual molecular masses. So example, like ionic solids, potassium chloride, NaNO3 in aqueous solution. So based on these abnormal molecular masses, we have one more factor called Van 't Hoff factor. If the solute is associated in a solution, the number of particles will be less than expected, and hence it leads to lower value of colligative property. The molecular mass calculated in such case will be more than the actual molecular mass. For example, benzoic acid in benzene. Benzoic acid means C6H5COOH. It forms ions, that is C6H5COO minus and H plus. C6H5COOH. So when benzoic acid is dissolved in benzene, what happens? C6H5COOH is benzoic acid. When it dissolves in water in benzene solution, it dissociates to form, giving rise to C6H5COO minus and H plus. So these ions we have to consider. So that is only we are getting abnormal molecular mass. Abnormal molecular mass. So the molecular mass of solute determined when it is either dissociated or associated in solution using colligative property measurement is known as abnormal molecular mass. So the molecular mass of solute determined when it is either dissociated or associated using colligative property measurement is known as abnormal molecular mass. So for this we have to consider one more factor called Van 't Hoff factor. So in order to determine the extent of dissociation or association, this is very, very important slide. Please note down your classwork. Very important for objective point of view. In order to determine the extent of dissociation or association, Van 't Hoff introduced a factor known as Van 't Hoff factor. This is denoted by the letter I, where I is equal to normal molecular mass by abnormal molecular mass and observed value of colligative property by normal value of colligative property. And I is also equal to total number of particles after dissociation or association by number of particles before dissociation or association. So this is called abnormal molecular mass, and it is nothing but denoted by the letter I, and it is calculated by using Van 't Hoff factor, that is I, where I is equal to normal molecular mass by abnormal molecular mass. I is equal to observed value of colligative property by normal value of colligative property. So when you will get this I factor, if a electrolyte is dissolved in a solution as a solute, then you will get, I'm writing it here, if electrolytes means like ionic solids, if electrolyte is dissolved in a solution, then we have to consider I factor. Then you have to consider I factor. I factor is important. So till now we have seen only non-electrolytes. Now we'll see what happens when electrolyte is dissolved in a solution. When an electrolyte is dissolved in a solution, they dissociates or associates into ions. And so the colligative properties will slightly change off. So to maintain that colligative property, they have used one more factor called Van 't Hoff factor, where I is equal to normal molecular mass by abnormal molecular mass. I is equal to observed value of colligative property by normal value of colligative property. And also I is equal to total number of particles after association or dissociation by total number of particles before dissociation or association. Let us see how this will work out. The value of I is less than 1 in case of association. Underline this. In case of association, the value of I should be less than 1 and more than 1 in case of dissociation. I is less than 1 in case of association and more than 1 in case of dissociation. Including the Van 't Hoff factors, the expression for colligative properties becomes, the relative lowering of vapor pressure becomes, yes, we have to multiply with I also. So P01, P1 naught minus P1 by P1 naught is equal to I into X2, that is mole fraction of solute. Similarly, delta TB is equal to I into KB into M, and depression freezing point I into KF into M, and osmotic pressure pi is equal to I into C into RT. So all these things I value you have to use, because if you take a electrolyte into dissolution. Next. So here now question now. 1.8 grams of benzoic acid dissolved in 25 grams of benzene shows a depression freezing point of 1.62 kelvins. Calculate percentage association of benzoic acid in benzene. They're asking us to find percentage association. Now 1.8 grams of benzoic acid. So weight of solute is called 1.8. But more important here it is they have given electrolyte, that is benzoic acid. So weight of solvent. They are showing depression freezing point. So delta TF is equal to I into Kf into M, where M is called molality. So how to calculate molality? I into, that is equal to I into Kf into weight of solute by molecular weight of solute into 1000 by weight of solvent. So if you substitute these formulas, definitely you'll get. What is the value of I for benzoic acid? Very, very important. For benzoic acid, I value is 2 because benzoic acid dissociates to form 6H5. Benzoic acid formula is C6H5 COOH, which is nothing but C6H5 CO minus plus H plus. So 1 plus 1, that is equal to I is equal to 2. So if they ask percentage of dissociation, then we have to take differently. But here they are asking I value. So straight away they have given all the values except no, all the values they have given. First you will find I value, then we will find percentage of dissociation. How to get percentage of dissociation also I tell you. First we will find I value. I is equal to. So in this sum, I value you have to find first. Don't write I is equal to here. Actual I value should be 2, but it should be less than 2. Then we can say percentage association of benzoic acid. So how to calculate percentage? First you calculate I from the formula. So I is equal to delta TF into molecular weight of solute into weight of solvent divided by Kf into weight of solute into 1000. So substituting these values, let us see. I is equal to delta TF is given how much? 1.62 K. Directly they are given depression freezing point into molecular weight of the solute. Molecular weight of solute benzoic acid C6H5COOH. So carbon 12, 12 6 is 72, 72 plus hydrogen 1, 77, hydrogen 1 into 5, 77, carbon 12 again 89, 89 plus 16, 105, 105 plus 16, 121, 121 plus 1, 122. So it is 122 into weight of solvent. Weight of solvent is given how much? 25 grams of benzene divided by Kf. Kf value is 5. Kf value is 5 into weight of solute 1.8 grams into weight of solvent, 1000. So 25,000, how many times? 40 times. So 40. So now the numerator what we have 1.66 into, I'm writing here 1.6 into 1.62 into 122 into 1, that is 197.64. Numerator value is 197.64 by denominator value 5 into 1.8, 5 into 1.8 into 40 is equal to 360. So 197.64 by 360, 197.64 by 360, which is equal to 0.549. So I value is equal to 0.549. Actual I value should be 2 if it is 100% dissociation. So 0.51 percentage of dissociation is equal to percentage of association is equal to, next line. So I'm taking new slide. I'm playing the drawing. Next percentage of association is equal to we got I value is equal to how much? 0.549. 549 divided by actual value of I for benzoic acid should be 2 into 100. So 0.549 into 100 by 2, 27.45%. So it is 27.45% is associated. So that is called alpha. That is percentage association. Alpha. How you can write for association? Alpha is equal to 1 minus x by 2 by 1. X is equal to 0.92. So first you will find I value as usual. M2 is equal to given. So first you will find I value. I is equal to 1 minus x by 2 by 1 because it is association, and you will get x value is equal to 0.902. I hope it is clear now. They are given I value only. Next, second example, 0.6 cc of acetic acid having density. Again, acetic acid formula is CHCOOH. CHCOOH is nothing but it is again acid electrolyte dissociates to form CH3COO minus and H plus, having density 1.6 grams per cc is dissolved in 1 liter of water. The dispersion freezing point is 0.0205 kelvins. Calculate the Van factor and dissociation constant of acetic acid. So to find dissociation constant, Ka is equal to Ca alpha square. C alpha square, that is Cx square. So M2 here, hint is what? M2 is equal to, first we find molecular weight of solute. So it is nothing but Kf into W2 into 1000 by W1 into delta Tf, and I is equal to 1 plus x by 1. X is called uh, number of ions. Number of ions for acetic acid becomes 2. X becomes number of ions. So K is equal to C alpha square. Then you will get the answer C alpha square by 1 plus alpha. C alpha square by 1 plus alpha. Then Ka value dissociation constant of acid becomes 1.69 10 to the power of minus 5. 1.69 10 to the power of minus 5. Before going to this, so here what they are given, depression freezing point is directly given delta Tf. Actually, delta Tf is equal to 0.0205 kelvins. They are given density. From density, you can find mass by volume. So that density is equal to mass by volume. You know mass and you can find out volume. They are given mass of acetic acid is, volume is given also. So you can find mass of acetic acid. So in this way, you'll find the answer. I hope it is clear. Next question. Some more questions I want to add for Van factor. How to solve it. Very, very important. So here I'm taking one more slide. Questions related to Van factor and abnormal molecular masses. So here, the value of Van factor. Van factor for potassium ferrocyanide. Calculate the value of I. Van factor. Calculate the value of I. Calculate the value of I. Value of I for potassium ferrocyanide. K4 FeCN taken 6 times. K4 FeCN taken 6 times. So this is called potassium ferrocyanide. So how to calculate I? Simple. Second one, this is first one. Now I'll do for at least 3 or 4 models, then you can understand easily how to calculate I. This is first one. Second one, sodium sulfate, Na2SO4. Third one, aluminum chloride, AlCl3. Fourth one, we can find sodium Na2SO4 is already over, no? Aluminum sulfate, Al2SO4 taken thrice. And fifth one, NaCl. So without any dissociation, just how to calculate I am showing. Afterwards, we'll see according with the dissociation also. That is percent of dissociation or association. So K4 FeCN taken 6 times. First one, I am solving it here. Just see it. Very, very important. K4 FeCN taken 6 times. This is a complex compound. FeCN taken 6 times, and for FeCN6 this big bracket will come because it is a complex compound. So it dissociates to form, K4 4K plus 4K plus FeCN taken 6 times minus FeCN taken 6 times whole complex minus. So I value is equal to 4 plus 1 because 4 moles of potassium, 1 mole of ferrocyanide ion. So 4 plus 1 it is equal to 5. Similarly, second one, sodium sulfate, Na2SO4. So dissociates to form 2Na plus SO4 2 minus. So it is 2 moles of sodium and 1 mole of sulfate ions. So it is I is equal to 3. Similarly, third one, AlCl3, dissociates to form Al plus 3 plus 3Cl minus, because valency of chlorine is minus 1. So 1 plus 3. So I value is equal to 4. Similarly, fourth one, Al2SO4 taken thrice. So dissociates to form 2Al plus 3 plus 3SO4 2 minus. So I value is equal to 2 plus 3. So we will not see charge, only the number of moles. I is equal to 5. Similarly, NaCl gives rise to Na plus Cl minus. That is 1 plus 1, it is equal to 2. So this is the I values if it is 100% ionized. Now, how to calculate next topic in this session now. So if it is 100% ionized, we can say I values like this. Now, next topic, how to calculate I value with respect to alpha, where alpha is called extent of dissociation or association. Extent of dissociation or association. So in case of dissociation, alpha is equal to, first case, in case of dissociation, alpha is equal to dissociation. Alpha is equal to 1 minus I by n minus 1. Where I is called Vanta factor, n is called number of ions. N is called what? Number of ions. So in case of association, alpha is equal to 1 minus n by 2. I minus 1 I minus 1 by 1 minus n by 2. So this is the formula for dissociation and association, and mostly we'll get for dissociation only. And now I'm doing calculation of I for all the sums which I have given now with respect to percentage of dissociation. Next, calculate the value of I if it is I of potassium ferrocyanate, calculate the value of I for potassium ferrocyanate, calculate the value of I for potassium ferrocyanate K4 FeCl taken 6 times complex compound. If it is 50% ionized, 50% ionized means here the percentage of dissociation is given. So alpha is equal to 0.5 because alpha is equal to 50 by 100. First we'll say alpha is equal to, since they are given 50% ionized, so alpha is equal to 50 by 100. Alpha is equal to 50 by 100. Alpha is equal to 50 by 100. That is equal to 0.5. So 0.5 is equal to I minus 1 is equal to I minus 1 by n minus 1. What is n here? N is equal to 5 because potassium ferrocyanide dissociates to form 4K plus FeCN taken 6 times minus. So it is equal to 5. So 0.5 into is equal to I minus 1 by 4 minus 1. Sorry, 5 minus 1. So it is 4. 4 into 0.5, that is equal to 2. So I minus 1 is equal to 2. Implies I is equal to 3. So 50% means don't take it is 2.5. Here I is equal to 3. In this way you have to calculate. I hope it is clear now. Next question. Calculate the value of Vanta factor. Calculate the value of I. Calculate the value of I for sodium sulfate. If it is 40% ionized. So again using the same formula. Now alpha is equal to 40 by 100, which is equal to 0.4. So 0.4 is equal to I minus 1 by n minus 1. So n value for sodium sulfate already you know it is 3. So 0.4 is equal to I minus 1 by 3 minus 1. So 0.8, I minus 1 is equal to 0.8 plus I is equal to 1 plus 0.8, that is 1.8. So I hope it is clear now. Now, how this Vanta factor is useful for calculating osmotic pressure or any other colligative properties. Now we are going to discuss that question now. Next question write down. A decimolar solution of potassium ferrocyanate. A decimolar solution of potassium ferrocyanate. K4 FeCN taken 6 times. This is previous NEET question. Just listen carefully. At 300 kelvins, is 50% dissociated. Then the osmotic pressure of the solution is osmotic pressure of the solution is first option 3.61 atmospheres, second option 7.38 atmospheres, third option 12.32 atmospheres, and fourth option 21.34 atmospheres. Let us see how we will solve this question. So already we know pi is equal to, since they have given electrolyte, first we have to see pi is equal to C into I into T. Pi is equal to I into C into RT. So if they have not given percentage of dissociation, directly I value is equal to 5 we can write. But since they have given percentage 50% dissociated, so first we will find I value for 50% dissociation. Then C value is also given, decimolar solution. Decimolar means 0.1. Decimolar means concentration becomes 0.1. So decimolar means concentration becomes 0.1. So To calculate value for I for potassium ferrocyanide, it is given already. We have seen in the last case. If it is 50%, I value is equal to 3. I value is equal to 3. So substituting, since I is equal to 3, pi is equal to 3 into 0.1 into R value, because decimolar solution, and R value is 2 into temperature is 300 kelvins. So multiplying this, so 3 into 0.1, 3 into 0.1 into 2 into 300 is equal to 180. Now 3 into 0.1 into R value is gas constant. So 1 second, let me check the R value. Gas constant value. So when atmosphere is given liters, 8.314, 8.314, when atmosphere is given, it should be 2. So you'll get R value 2 only, 1.98 for liter atmosphere, liter stars, liter atmosphere, we have to use R values 1.98 only, that is 2 only. So 3 into 0.1 decimolar solution means here decimolar means 0.1 equals 10 to the power of minus 1. Let me check. Decimolar solution. Decimolar is m by 10, that is 0.1. They have given molarity also. And then the pi of solution, pi is equal to I into CRT. So C is given 0.1, I value is 3, and 2 into 300. So it should be 180 atmospheres. So I think the option is given wrong. The osmotic pressure pi is equal to 0. Osmotic pressure pi is equal to I into C into RT. So I value we already got, that is 3 well, and C is equal to 0.1. I value is 300%, it is correct. R value is also 1.98 or 2. So instead of 1.98, I have taken 2, it is also correct. So 300. So here R value should take it as 0.0821. Just note down. R value don't take 2. In all the cases, you have to take R value 0.0821. Now I understood. So 0.0821. R value take 0.0821. Now we multiply 3 into 0.1 because they are given in atmospheres. So 3 into 0.1 into 0.0821 into R value 0.081 into 300, which is coming around 7.38. Now we got the answer. So 0.0821 is equal to 7.38 atmospheres. So in all the cases, R value you take it as 0.0821 for osmotic pressure. So R value is 0.0821 for osmotic pressure. In case of calories, we have to take R value is equal to, so here it is atmospheres. So it is taken as 7.38 answer. So R value is 0.0821. Next question. Next we will solve for osmotic pressure questions also. Calculate the osmotic pressure of 5% aqueous solution of sugar. Calculate the osmotic pressure of 5% aqueous solution of sugar. Osmotic pressure of 5% aqueous solution of sugar with molecular mass. Aqueous solution of sugar with molecular mass 342. With molecular mass 342. At 15 degrees C. So here sugar is non-electrolyte, so no need to take I value. Yes, we are doing some more questions based on osmotic pressure. So pi is equal to C into R into T. They have given 5% aqueous solution, that is 5% weight by volume they have given. So 5 ml dissolved in 95 ml. So 5% aqueous solution is 5 grams is dissolved in 5 grams of sugar, that is 5 grams of sugar. So 5% aqueous solution means 5% aqueous solution means 5 grams of sugar. Aqueous solution means this typical volumes is important. 5% aqueous solution means 5 grams of sugar is dissolved in 100 ml of water. 100 ml of water. So now substituting this problem, pi is equal to C is given how much? C we have to find out. So weight of solute, that is weight of solute is given 5 grams. 5 grams by molecular weight of solute, that is 342 into 1000. 340 is given into 1000 by weight of volume. Volume is given 100 ml into R value 0.0821 into temperature is 15 degrees C, that is 273 plus 15, 298. Sorry, 288. 288 kelvins. So you have to convert the temperature into kelvins, and R value always you should take 0.0821. That is very, very important. Now let us see the calculation part. So 5 into 10, 50. So 50 into 0.0821, 50 into 0.0821 into 288 is equal to 1182. Numerator part is 1182. 1182.24 divided by 342, which is coming around 3.54 atmospheres. 3.54, sorry, 3.45. 3.45 atmospheres. 3.45 atmospheres. So this is the answer. So in the previous case also, pi value you have to take it as 0.02. That's why we have got percentage more percentage. So in that case, you rectify that problem. R value you should take it as 0.081, not 2. So just rectify that in the previous questions. Only one question we have discussed like that, but all the questions R value is 0.081 in case of pi, that is osmotic pressure. I hope this is clear. So today we discussed, in this lecture, we discussed about the fourth Colligative property and also abnormal molecular masses, that is Van 't Hoff factor. So Van 't Hoff factor, how to calculate also I have shown. So Van 't Hoff factor I values is also important. So Van 't Hoff factor. So next class we'll discuss summary of the topic and entire chapter important models. I hope it is clear now. So now we are ending this session. Thank you.